Hello, everybody. This is Jared McShane. I'll be doing a short presentation on using encryption to share files on the IPFS network. Okay, so what is IPFS? It stands for Interplanetary File System. It's a framework for hypermedia storage and transfer. A lot of ways it's similar to HTTP, except it has a few key differences. One, it's a peer-to-peer network. That means no node or no servers or nothing is privileged amongst any other node in the network. Content is retrievable by a content address. So in HTTP, we have URLs. What that stands for is Uniform Resource Locator. So that gets translated through DNS to an IP address. So when you want to get content from our URL, if that content has changed locations, then that URL might be broken and you might not get your content. However, in IPFS, they use something called content addressing, which means if you want to get your content, all you have to do is pass in the content identifier, which in a lot of ways is just a hash of that content. So you just say IPFS get this content, and it'll, through distributed hash tables, retrieve all your content from the peers, which leads me to my next point. One, you can think of it as a distributed file system. So on your computer, you have, your file system, but this is kind of a file system amongst a whole bunch of peers on the network. And another thing to note on that is that one single file may be stored in chunks across the network. So your file can be broken up into small bits, and one peer stores one bit, another peer stores another bit. And when you retrieve it through the distributed hash table, all of that stuff gets forwarded to you. Okay. So then how is data processed into IPFS? How is this data stored, linked together? How can we hash large files? So IPFS uses a Merkle DAG inspired from Git. So DAG is a directed acyclic graph. Think of it as a tree structure, except any node could have more than one parent node. So we have, this is a standard way that Merkle DAGs are created, although they will each be pretty unique. So I'll come back to this slide once we talk about the chunking. So we have one cat photo, and then we chunk it up into blocks, and then we hash the blocks, and we get a CID. So each node has a CID, which is essentially just a hash of the content of that node. So yes, chunk the data into blocks, hash the blocks. A node is equal to the data stored inside plus links to other child nodes. So here, let's say this node only contains the data hello world, but this node over here contains data, which is the metadata for this file, big file.js, plus it has hash links to all of these subnodes. So then these nodes will contain the data for the file. Another thing to note while I'm here is you see this node has two parents, and it is hello text in this directory, and in my directory, it's also my file text. So this is called deduplication. So if a chunker sees that one file has multiple links, then it can not duplicate. So if this file is multiple places in this folder overall, then it can just link it twice. It doesn't have to store that file twice, like most file systems would, because it's hash linked. It has that advantage. So yeah, the chunker will link the hash of the node's content, and it'll create parent nodes and layers. So you first create all of the base layers, and then you can create the parent ones after that. And then each file will have a unique root CID. So once you concatenate and you hash up, so you'll hash these and then you'll get this node, and then you hash all these together and you get that node, and this is the root file CID. So when I speak of the CID of the file, it's the root node. Okay, so some notes on the Merkle DAG and chunking. Not all chunkers are the same. There's a lot of different variables that go into it. You can pick a block size, data encoding. You can pick different hash algorithms. And it just varies a lot on factors such as file type. For one file type, you may want a block size of some number or a different number depending on the file type. And depending on that file type, you may want to implement different deduplication optimizations. So some other notes: every node in a Merkle DAG is a root of a sub-Merkle DAG, just like a tree. Merkle DAG nodes are immutable. So if you change this data right here or here, these parent nodes will have to change because this hash will change because the hash of the data will be different. And then you have to update the hash length, which means that this content is different, which means you have to update this hash, which means you have to update this hash and that content. So it chains upwards. However, IPFS does implement a mutable file system on the client side that you can interact with the IPFS network. So yes, two nodes with the same CID must mean the nodes are identical due to hashing. So this implements a challenge of security. Any node, since your data is going to be chunked up into blocks and distributed, if anybody has your block, they can read what's inside your block. Or if anybody gets the CID of your data, and they can just retrieve the entire file. There is no built-in encryption to IPFS, so your files are not secure or private. So how do we solve that? There's some other people have done a lot of work on this, mostly using a blockchain and an access control list. So you'll have a smart contract on the blockchain, which can determine, which can grant access based on a variety of different implementations. So these researchers have implemented with public keys and attribute-based encryption, and they use tokens. I won't get into that too much, but there's references on the last slide. So what I've implemented is just using hybrid encryption. So we encrypt our file with symmetric encryption using a secret key, and then we use asymmetric key RSA encryption to share that secret key. So these are the steps. I won't go through them due to time. I just want to get into the demo. So here are the references that I've used. Okay, so let's get into the demo. So in this, all right, so this will be just a short demo. So I have SSH'd into my Raspberry Pi that's connected through Wi-Fi, and then this is my desktop computer terminal right here. So let's take a look. I will transfer mountwhitney.jpg, crypt it, put it on IPFS, and then decrypt it on this side, or retrieve it from IPFS, then decrypt it. So as you can see, it's not here. So to start this, we run encrypt.py. Okay, then over here, we run decrypt.py. And now that sends over the public key. So now we need to enter what file we want to share. Okay, and now you see this is the CID that we've generated. So this is the root CID of the Merkle DAG. Okay, so that seems like it worked. Let's go ahead and take a look here. Right here. It's in fall research. Okay, so it'll be decrypted file. We need to rename it so that it has a proper file extension. Then we can open it up, and we see that'll work. And this file's pretty large, so almost 3 megabytes. So, it works on pretty large files, and there's no reason it wouldn't work on even larger files. So if you have any questions, you can email me at jaredmcshane@gmail.com. If you want to see the source code, I'd be happy to share it. All right. Thanks for watching.